This is not a rotational solid, so you're just finding the area. So it's just this integral right here. It's just that integral right there, Liv. You're integrating from -1 to 5 of the upper bound. That's it. So that's the two-dimensional. It's just doing it by hand. You're doing it by hand. That's it. This is just the area, so it's two-dimension. You're not doing volume. Volume is later when you start rotating in like that one or 3, 4, 5. Yeah.
Do we always have to?
You're going to want to do something like, okay, I know the function does this, so when I do 180 degrees, it'll be this, and one of the disks will be like this, right? It's important, or if I'm sorry, I'm drawing this without actually being at the board. So like, there's one of the disks, right? Yeah, it just opens up a little bit. You see what I'm trying to draw right there? Yay, nice. It's really helpful because later in this class and in future calculus classes, it's not always obvious what it looks like. It's not always obvious. Sometimes you're going to learn how to rotate around the y-axis, for example. It's really important to do this because what is this distance right here that I'm shading right there? What's that distance called? That is d what? That's dx, right? So sometimes you're going to do dy, then you get to multivariable calculus, you'll dz. It doesn't seem as necessary now because we're in 2 dimensions, spinning into 3 around just one axis. It'll be more important later. So basically do the easy stuff to be helpful to yourself, I guess is the way to put it. But no, it's not required. It's rotating around the x-axis, so that's the bottom reflection of it. So that's point A. What's point B? B is 0. Sorry, is B. What point is B? It's up on the board, kids, so it shouldn't be that hard to answer. What is B? Pi, comma 1. And what's C? 2 pi, comma 7. Right, exactly. So then if you drew one slice, which you're going to have to do, you take one rectangle like this. It's going to go down like this. And then what's that going to rotate and look like? It'll look like this. So there's one disk. How many disks are there theoretically? How many disks? There's an infinite number. So this would be your integral. How many people agree that that's the integral right there? How does that look? Is that pretty good? Now, if you had to do this integral, if I said to compute this integral, what might you try? What might you try? What's one method you could try? You have very few methods for integration. What's one? W substitution. But what's the challenge with W substitution on this one? There's no real, you don't see anything, right? Because what are you looking for? You're looking for a function who also has its what there? Yeah, do you see a function in its derivative? So you have right now, you have basically like by hand, just know what the integral is. You have W substitution, right? And you could also expand it, right? Now, could you multiply this out? Sure. But why doesn't that really help you too much? There's going to be a term in there that's really not something you want to ever have to integrate in this class. If you multiply that out, 3 cosine W plus 4 times 3 cosine W plus 4. Oh, x, sorry. Yeah. What would be the term in the product that you really wouldn't want to have to integrate? Cosine squared. Yeah, you really don't want to have to integrate cosine squared. It looks like it's, oh, there must be a really easy way to do it. It's not fun. So what do you think you have to use on this?
Can you just put W back in?
Oh, I erased it and then put W back in. I did. Sorry. I did. I really like W substitution. And I'm getting judged a little bit. Getting judged. Yeah, so what I'm telling you is, what do you think the only way to solve this is for you? For you. What do you have to use? Nope. Again, you can't expand it. You have to use a calculator. Do that right now. Tell me what this comes out to be to 3 decimal places or in terms of pi. I want the answer in terms of pi, and I want the decimal answer. I want the decimal. What? Because remember, it's pi r squared h. Pi r squared h. So the pi is right there. The r is right there. And the h is right there. That's where it is. We left off the square, and then you get to 25 times, right? It's going to be bigger. It's going to be bigger. Okay, so let's make it a little easier then. Let's make it a little easier. Can you please sketch me this shape? Sketch me that 3-dimensional shape. That's what I want you to see. Dx. Just the integral of dx. So what's the integral of 1, effectively, Liam? What's the integral of 1? If you integrate 1, what do you get? Yeah. So you get 25 pi x from 0 to 4. So that's going to be 25 pi times 4 minus 0. So what is that? 100 pi. So that's using calculus. Yes.
Why doesn't the
integral of a times x dx is a times the integral of x dx. So in this case, there's no x in there, so the x is gone. It's just dx.
Yeah.
It's also not plus, it's multiplied. Yeah. Draw me what's going on in C. Do not integrate or 0. That point reflects right there. So like what's the, oh, there's one circle. Here's another one, right? Here would be another one. So what kind of shape would this be if you looked at it from the side, like tilt your head to the left? What would you shape? What shape would you see? It's like a tilted cone. It's like they were calling it a volcano, like it's a volcano. It's got a flat front like this, right? Kind of got a shape. What happens as I draw more and more lines? It's kind of harder to see in a way, right? Kind of harder to see. What? I'm sure there is. I'm sure there is a technical name. I don't know what it is. Not sure what it is. This is key, be very careful about this. What is the integral that we need to write? What is the integral? What's the lower limit of integration, Mikey? Like, what are the limits of integration here and here? What's the farthest to the left it goes? What's the farthest to the left it goes? 0. And what's the farthest to the right? 3. And it's going to be pi. I'll pull the pi out just to the front. R squared, and it's not h, we write dx. The key here is, what is r in this case? What is r? What do you think it is, Sarah?
It's like the distance between
Yes.
-2
Yes, r is right there, that purple right there. You see that purple I just drew in there? So, can someone tell me what it's going to be? What statement will represent r? Well, what's the distance? What's the distance from here to here? What's that distance? X squared minus what? Minus what? Careful. Minus -2. I'm writing it that way so you can see where it's coming from. What's the distance from 5 to 3? How'd you get 2? 5 minus. What's the distance from 5 to -2? 5 minus -2, right? If you have two numbers, how do you find the distance between them? You subtract the smaller from the larger regardless of sign, right? Everybody with me so far? So, what do we plug in there? If we want to write it nicely, what do we plug in? So it's going to be pi integral 0 to 3 x squared plus 2 squared dx. This would be the integral you would evaluate right there. Yes, Sarah? Well, you can do it either substitution or what? Or what? Or expand it. Let's expand it, shall we? So what do we end up with? Pi 0 to 3. Can someone just tell me what it expands to who hasn't spoken yet? Like what does that expand to? Just tell me. Integrate that for me. What does that integrate to? X to the
5/5.
Uh-huh.
That's 4x³ / 3.
Yep. And you're doing that one from 0 to 3. At least it's 0, right? Do you like 0? Yeah. I like 0. So what does that come out to be? Pi times 3 to the 5th over 5 plus 4 times 3 to the 3rd over 3. So can you do this one technically by hand? Yeah. Is it kind of annoying? Yeah, 243 over 5 plus 36 plus 12 is pi times 243 over 5 plus 48. You need a common denominator, right? Like, this is not super fun, but is it necessary you know how to do this? You need a common denominator, so what's that going to be? What, 240 over 5? Is that right? Yeah? So what do you end up with? 483 over 5 times pi. Is that a lot of algebra? And did I do that very, very quickly? Yes, but the point is this. Do you understand each step that I took to get there? The height of each slice, this right here, you see what I'm doing right there? That distance is dx. This disk right here that we're adding together is infinitesimally short. Yeah, it's a Riemann short, exactly. The height is dx.
Wait, so how do we decide, how do we figure out or decide what dx is?
Dx is always the little infinitesimal piece.
What does that translate to when you integrate it?
The dx. It is the dx.
I mean, when you write out the antiderivative.
We added together an infinite number of what? Rectangles, right? The height of each rectangle was what? F of x, and the base of each rectangle was what? Dx. So this means literally adding together a lot of rectangles, right? That's what that means. What are we doing now? We're doing the same thing, but we're taking each of these rectangles and doing what with them? Spinning them, right? And what do they turn into? They turn into discs, right? They turn into discs. So you have a disc like this. What's the volume of that disc? R and h. It's pi r squared times h. But what are we calling this height? Dx. So we're integrating this right there. That's what we're integrating. We're adding together an infinite number of disks that have heights dx. And it's really important that you realize that that's dx, because here's the thing. If we were to rotate this instead around the y-axis, are we going to be using dx? No, we're going to be using dy. Actually, it doesn't change the math at all, because do we care what it doesn't change the math, it changes the integral. But, for example, we used x all over the place here. Does the math change if I change it to q? No, it doesn't. So we're going to change the value, but visualizing what happens is different than actually writing the integral. What I mean by that is this. This is just a preview. You don't need to write this down or remember it right now. But if I said x squared like this, where did we just rotate that? We just rotated across the x-axis, right? Where could we rotate it instead?
Around the Y.
We could rotate it around the y-axis. And then do we still get these disks? Yeah, we still get the disks. And what are you going to do? You're going to integrate from, let's say, I don't know, let's say it's to y equals 10. I'm making this up, okay? 0 to 10, it's going to be pi r squared dy. So if you're doing dy, what does r have to be in terms of? Not x, it has to be in terms of, because, exactly. So all you have to do is make sure you're writing it in the right variable, and then the same calculus kicks in. We're not doing that yet, we're doing one perspective at a time. That volume is very different than before, right?
Yeah.
It's the sideways volcano as opposed to like a parabolic bowl. Very different, very different.
So